Welcome back to Fundamentals of AC Circuits. In this video, we're going to discuss series RL circuits and parallel RL circuits. So the purpose of this video is that you'll be able to describe the sinusoidal response of RL circuits, calculate the total impedance of an RL circuit, be able to apply Ohm's law to an RL circuit, and then analyze a series RL circuit, both lag and lead circuits, as well as an RL parallel circuit. So we've already discussed RC circuits, both series RC circuits and parallel RC circuits. We've also discussed series parallel RC circuits. Now we're going to look at those same types of circuits, but replace the capacitor with an inductor. So look at the screen and you'll see that there is a basic series RL circuit shown. You have your AC source providing a voltage wave to the circuit. And with an RL circuit, we're going to see some different relationships as compared to an RC circuit. So as a reminder, when a circuit is purely resistive, the phase angle between the source voltage and the total current is 0 degrees. But when you have a purely inductive circuit, the phase angle between the source voltage and the total current is 90 degrees. Therefore, an RL circuit will have a total current that has a phase angle that lies somewhere in between that 0 degrees that would be for a purely resistive circuit and the 90 degrees that you would see for a purely inductive circuit. So when we have an RL circuit, here are some of the relationships that we're going to see. If you look at the voltage across the resistor, the voltage across the resistor is going to lag the source. The voltage across the inductor will lead the source. The current in the circuit will lag the voltage. These are the relationships that you are going to observe, and the reason why we need to know these relationships is because it helps us to check our work. If I know that the voltage across the resistor should lag the source, when I actually calculate this resistor, the voltage across this resistor, and I look at that phase angle should be negative. If it's not negative, then I know I've done something wrong, because this relationship will always be true in an RL circuit. So just as a quick comparison, on the left is an RL circuit, and on the right is an RC circuit. And now we can see how these relationships change. In an RL circuit, the voltage across the resistor will lag the source, but in a RC circuit, that voltage will lead. The voltage across the inductor is going to lead the source. The voltage across the capacitor is going to lag. Notice that we have basically inverse relationships between an RL circuit and an RC circuit. So when it comes to calculating impedance of an RL circuit, remember impedance is the idea of an opposition to AC signal. We know that in a purely resistive circuit, impedance is resistance. In an inductive circuit, your impedance is your inductive reactance. In an RL circuit, impedance is determined by combining your resistance value and your inductive reactance values. So your total impedance of an RL series circuit is expressed as R plus JXL. So we know for an RC circuit, our total impedance was R minus JXC. For an inductive circuit, where you have a resistor in series with an inductor, your total impedance is R plus JXL. So we can draw an impedance triangle for an RL circuit in the same way that we can draw an impedance triangle for an RC circuit. R is plotted along the positive x-axis. XL is plotted along the positive y-axis because it's a plus J term. With the impedance of series RC circuits, we saw the XC value drawn below the x-axis. It was drawn down here. With an inductive circuit, we're going to draw it above the x-axis because we have a positive J term. And then your total impedance is the diagonal between these two vectors. And the angle between the origin and your impedance is determined by the inverse tangent of XL over R. So we can take these vectors, which represent the idea of total impedance for a series RL circuit, and redraw them to form what we call the impedance triangle. Remember that we're going to originally write out the total impedance of a series RL circuit in rectangular form by writing the value for R and the value for XL, and then we're going to convert that to polar by basically figuring out the length of this hypotenuse of the impedance triangle and the angle theta. So when we think about series RL circuits, we can apply Ohm's law the same way we've applied it to every other circuit in this course. You're going to start by finding total impedance. Once you do, that total impedance is what you're going to use in your Ohm's law equation. You know you have the same current everywhere in a series circuit, so you can simply manipulate this equation to find the value that you need. An RL lead circuit is a phase shift circuit where the output voltage is going to lead the input voltage by a specific amount. An RL lead circuit is formed by having a resistor in series with your source, and following that is an inductor, and we're going to measure the voltage across the inductor as the output voltage. In the middle, in image B, you'll see a phasor diagram showing the output voltage, which is going to lead the input voltage. So here's the voltage across the resistor. Here's the input voltage. Here's the output voltage that you'll see across the inductor, and it will have a phase lead of some amount we call phi. And if you were to graph these phasors, because remember, every phasor diagram is just a shorthand way of drawing a series of sine waves. If we were to graph our phasor diagram and show the input and output voltage waveforms, here's what it might look like. Here's our input voltage. Here's our output voltage with a leading phase angle of phi, some amount of phase angle here. So now let's go ahead and analyze an RL lead circuit. So for the circuit shown, we know that the input is 5 and an angle of 0 degrees. We're going to calculate the total impedance, the total current, the voltage drop across each component, and we're going to write everything in polar form. Then we're going to draw a phasor diagram for the voltages in the circuit and determine the amount of phase lead for the output voltage. Now remember, this is a series circuit. These terminals here just represent the idea of the alligator clips you would have on a DMM, or the probes you would use from an oscilloscope. So this is just where we would connect the probes. This is a series circuit where current is flowing through R, through L, and then back to the source. So let's start with total impedance. We're going to use the formula provided for total impedance, which is R plus JXL. So remember, you have to first go and calculate XL. And XL is calculated by doing 2 pi FL. There's your formula. So we're going to plug in the 1 kilohertz frequency provided as well as the 50 millihenries provided to get our XL. Once you have XL, you can plug that into your equation for total impedance. So basically we add together these two impedance values for an RL circuit. So we have R plus JXL and convert that to polar form right here. Now we can use the total impedance and Ohm's law to find the total current in the circuit. So we're going to perform this division, 5 at an angle of 0 degrees volts, divided by 749.06 at an angle of 24.08 degrees ohms. And you'll get your total current in the circuit. Remember, we're going to divide the magnitudes, subtract the angles. So we have 0 minus 24.8 gives you a negative 24.8. If you remember a few slides ago, we discussed the fact that the total current is going to lag the source in an RL series circuit, and that's exactly what this means, that the total current is lagging the source by 24.8 degrees. Then we're going to use Ohm's law to find the voltage across each component. So we're going to take that total current and multiply by the impedance value for the resistor, which is 680 ohms at an angle of 0 degrees. We're also going to use Ohm's law to find the voltage across the inductor by taking the total current and multiplying that by the inductive reactance written in polar form. Now notice that the inductive reactance written in polar form is right here, 314.16 ohms at an angle of, look at this here, positive 90 degrees. With a capacitor, if we were writing the capacitive reactance of a component in polar form, the angle was always negative 90 degrees. With an inductor, it's positive 90 degrees. If you think back to this term right here, our inductive reactance is plus JXL. And so if you convert that from rectangular to polar form, you get an angle of positive 90 degrees. So now we have our inductive reactance written in polar form multiplied by the total current in the circuit to give you the voltage for the inductor. So we can see that the output voltage leads by 65.2 degrees. Remember, our output voltage is the voltage taken across the inductor. The voltage across the inductor is 2.1 at an angle of positive 65.2 degrees. That means this leads by 65.2 degrees. That's why this is called a lead circuit. So again, if we were to graph the sine waves that we would measure for the source, the resistor, and the inductor, here's what it might look like. Here's our reference. That's the source. And our inductor is going to lead by 65 degrees. So our inductor may look something like this, where this distance here is our 65 degrees. And we also have the voltage across the resistor, which is lagging the source by nearly 25 degrees. So the voltage across the resistor may be about here, where this distance from here to here is 25 degrees. So when we make these calculations, it may feel like just a bunch of numbers, but it's always important to relate those numbers back to sine waves and what we're actually going to measure when we build a circuit like this on the bench. So if you were able to build this on the bench, or if you build it in multisim, this is what you'll see. And then the other thing you'll see is that the peak value of each sine wave will match the magnitude of your phasor. So the peak value of the blue sine wave for the inductor will be 2.1 volts. The peak value for the source will be 5, because that was what was given. And then the peak value for the resistor will be 4.54 volts. Obviously, I just drew this freehand very quickly. I didn't draw it to scale, but if you were to build this in multisim or measure this on a bench, that is what you would observe. All right, let me erase my drawing so I can show you the phasor diagram. Okay, and here's our phasor diagram showing the voltage for the inductor, the voltage for the resistor, and the voltage for the source. And we can see that there is a 90-degree relationship between the voltage for the inductor and the voltage for the resistor. If you remember looking at RC circuits, the voltage for the capacitor was the one that was below the x-axis, and the voltage for the resistor was the one that's above. Now these relationships have been reversed because of the nature of adding an inductor to your circuit versus having a capacitor. An RL lag circuit is a phase shift circuit, in which in this case the output is now going to lag the input. We create an RL lag circuit by reversing the inductor and the resistor, so that now the resistor is the component we're going to measure the output voltage across, which is right here. And when we build a circuit like this, we will see that the output is going to lag the input by a certain amount. So when we draw a phasor diagram showing the voltages, here's our output voltage across R, the input voltage will be leading, and your inductor voltage will be here, forming a 90-degree angle between your inductor and output voltages. And then if we were to draw a graph of the input and the output, you would see that the output lags by some amount we call phi. That's your phase shift. So here's an RL lag circuit. And for the circuit shown, the input voltage is 10 at an angle of 0 degrees, and we're going to repeat the same steps as the problem before. We're going to calculate total impedance, total current, the voltage across R, and the voltage across L. If you feel like you know what you're doing at this point, that's great, and I encourage you to hit pause right now and do this problem completely on your own. Then come back and check in for the answers. So to begin this problem, we're going to find the total impedance, and in order to do that, we need to have the inductive reactance, 2 pi FL. So we're going to calculate that first, and then we're going to plug that in to our equation for total impedance, R plus JXL. And that's going to give you approximately 1.18 kiloohms at an angle of 32.14 degrees. Then we can calculate the total current. 10 at an angle of 0 degrees divided by 1.18 at an angle of 32.14 degrees gives you your total current in the circuit. Then we're going to use Ohm's law to find the voltages across R and L, just like we did in the previous problem. And these are the voltages you'll get. So our V out is going to be the same as our voltage across the resistor, and we can see right here that output voltage has a negative phase angle, so it's lagging. It's lagging. That's why we call this a lag circuit. The output lags by 32.14 degrees. And there's my phasor diagram showing our three voltages. Now we're going to move on to parallel RL circuits. To calculate the impedance of a parallel RL circuit, we can use this equation on the screen. So the total impedance for a resistor in parallel with an inductor is R times XL divided by the square root of the sum of R squared plus XL squared. Your phase angle is the inverse tangent of R divided by XL. Notice that this is positive. In a parallel RC circuit, we saw that the phase angle was negative. So just keep in mind that this phase angle is now positive. In a parallel RL circuit, the source voltage appears across both the inductor and the resistor, so they are all in phase and of the same magnitude. Basically, all three of these components, the source, the resistor, and the inductor, they're all in parallel, so we know the voltage across each of those components. What we don't necessarily know is the current. The current's going to split between the resistor and the inductor, and what we're going to see is that the current is going to be in phase with the voltage, so the phase angle for your resistor current will be 0 degrees, and your current through the inductor will lag by 90 degrees. And then your total current will lie somewhere in between these two vectors, forming a right triangle. So let's look at a parallel RL circuit. For the circuit shown, we're going to calculate total impedance, total current, the current through R, and the current through L. Everything in polar form. And then we're going to draw a phasor diagram for all of the voltages and the currents in the circuit. Let's start with total impedance. And before you can do that, you need inductive reactance. So calculate that first, 2 pi FL. Once you have that, you can calculate total impedance using the formula provided on the previous screen. We're going to plug in our values for R and XL, and we're going to calculate the total impedance to be 1.19 at an angle of 57.34 degrees kiloohms. Now that you have the total impedance, calculate the total current. The voltage for the source was given as 10 at an angle of 0. Divide that by your impedance to get your total current. Now we can find the current through R. Because R is in parallel with the source, we know the voltage across R. So I'm going to use Ohm's law and take the voltage across R divided by the value of R to find the current through R. Remember, we're going to write everything in polar form here. So our impedance for the resistor is 2.2 at an angle of 0 degrees, and the unit for that is kiloohms. So there's our current through R. I'm going to use Ohm's law as well to find the current for the inductor. Remember, when you write the impedance for the inductor, you're going to take the inductive reactance at an angle of positive 90 degrees. And there's our current through the inductor. And finally, we're going to draw the phasor diagram. So first, here's my voltages. The source, the resistor, and the inductor all have the same voltage, 10 at an angle of 0 degrees. That's the black vector. Then we have our resistor current, which is in phase with the source. That's what we expected to happen. We have our inductor current, which lags by 90 degrees. Also, what we expected to happen based on the relationships provided. And then the total current lies somewhere in the middle with a phase angle that is negative, indicating that the total current is lagging the source as well by 57.34 degrees. And this is how we analyze a parallel RL circuit. So that sums up the techniques we're going to use to look at series RL circuits and parallel RL circuits. Up next, we're going to look at series parallel RL circuits. And then from there, we're going to put everything together and look at a series parallel RLC circuit. And that is the end of this video.